look at review on vector calculus. This is number 19. What we need to do is we need to show that there's no vector field G such that curl of G will be such this one. In order for us to show that there is no such vector, what we need to do is this. For any vector out there, div of curl will be equal to 0. Now, if you're curious, what you can do is you can let a vector to be equal to P, Q, R, assuming that P, Q, R are all functions of X, Y, Z. And I want you to take the curl of this and then take the divergence of that. Then you will realize that that's equal to 0. So what I'm going to do is to show that if this one, if there's such vector where curl is this, what I'm going to do is I'm going to get the divergence of this. So as here, then what is that equal to? Partial against x becomes 2, and then against y becomes plus 3z. Against z becomes minus 2xz. Is that equal to 0? No, they're not. So therefore, there is no such vector field G where the curl becomes this way. Alrighty, let's look at the second question. Number 25. Find the area of the surface. Now, how do you find the area? Okay, what we have to do is we just have to do the surface integral of ds. And you know that this, in fact, is equal to, especially if it's solved for z here, that's equal to partial z against x. Technically, there's negative sign, but when you square them, it doesn't, make any difference. And partial z against y, same thing. There's supposed to be negative sign in the front, but when you square that, it doesn't mean anything anyway. So we can ignore that, and then plus 1, and then dA. So now that's the idea. But let's try to plot these values here: 0, 0, 1, 0, and 2 zeros. Let us say it's right over here. That triangle is our domain. Then you can see that x can be expressed from 0 to the 1, and y can be expressed from 0 to the 2x, because this equation would have been y equals 2x. So what we're going to be doing is I can rewrite this one as 0 to the 1, 0 to the 2x. Partial against x becomes 2x squared, so we get 4x squared, plus partial against y, which is 2 squared, becomes 4, and plus 1, dy dx. But when you look at it, oh, it's nice because I don't have any y term here, y factor. So when I integrate this one against y, because then in that case I'm just going to attach y, and 2x minus 0 becomes simply 2x. So what we end up getting is 2x, 4x squared plus 5 dx. All right, then in this case, to evaluate this one, I'm going to set u as 4x squared plus 5. Then we get du equals 8x dx rather. So then I can rewrite this in this way. 1/4, because 2 was already there. Square root of u du. Then I get 1/4. When you integrate this one, we get 2/3. And u to the 3 over 2 pi. In other words, 1/6. U is 4x squared plus 5. So 3 over 2 power, that goes from 0 to the 1. So when you plug in the 1, what do we get? We get 9. Square root of 9 here becomes 3, so we get 1/6 and 27. But when you plug in 0, it becomes 5. So 5 to the 3 over 2 power is 5 radical 5. So minus 5 radical 5 becomes our answer. Alrighty, that was nice. Let's look at the next question. Number 27. So what we want to do is we want to get the surface integral where z is the or as an example, it can be density function. So how are we going to do this? All right, so z is equal to x squared plus y squared. So I can rewrite this one as x squared plus y squared partial against x, which is 2x squared, and I get 4x squared. Partial against y squared, which is 2y squared, we get 4y squared plus 1. And then dA. But wait a minute. On that paraboloid, when z is equal to 4, then our domain now becomes x squared plus y squared is less than or equal to 4. So, okay. This is clearly calling polar context. So what we're going to be doing is 0 to the 2 for r, and then 0 to the 2 pi for theta. So we get r squared, and then here we get square root of 4r squared plus 1, and r drd theta. How about that? Then we can rewrite this one as 0 to the 2 pi, 0 to the 2 r cubed, 4r squared plus 1, drd theta. Of course, you know what these two becomes. They are simply 2 pi. So I'm going to write it down on the side anyway. How about here inside? Oh, wait a minute. Oh, wait. We could set u as 4r squared plus 1. You probably, assume that anyway. But you get to realize that the u equals 8r dr. So one of the r can be used to be part of the du. But I have r squared left. Oh, r squared can be easily manipulated from the first equation. You see, r squared is equal to u minus 1 over 4. You see? So if I were to put that in place of r squared, so what we end up getting is, because I didn't have 8, so I'm going to have 1 over 8. And I have r squared left, which is u minus 1 over 4, and square root of u du. That's what I'm getting. Then I'm going to bring out 1/4, and then cancels with 2, so we get pi over 16. And then here we get u to the 3 over 2 power minus u to the 1/2 power du. So when you integrate this one, pi over 16, and we have 2/5. But what was u? U was 4r squared plus 1, so we have 4r squared plus 1 to the 5 over 2 power. And then minus 2/3 4r squared plus 1, 3 over 2 power, from 0 to the 2. So let's plug in 2 here. And pi over actually was a 16. So pi over 16 stays there. Then we have 2/5 times, it becomes 17 squared. So we get 289 square root of 17 minus, here we get 2/3, and then 7. So 17 square root of 17. That's the first portion. Minus, when you plug in 0, we get 2/5 minus 2/3. Alrighty. A lot to calculate here. So then, for the first one, when you combine these two things together, becomes pi over 16 was there. 1564 over 15 square root of 17. And then second one is minus, so it becomes plus 4 over 15. Now, interestingly, 4 cancels away. And this one becomes 391. And then when you factor out 1 over 15, so we get pi over 60. 391 square root of 17 plus 1 becomes our final answer. Whoosh. All right, let's look at the next question. Number 29. So what they want us to do is they want us to get the flux over the sphere. Okay, flux over the sphere. Then you know what? Since it's enclosed surface, what we can do is we can use the divergence theorem. So flux of the surface can be expressed as a divergence of the space inside. So what I'm going to do is I'm going to try to get this one. Triple integral of the div f dv. So then what is div f here? Partial against x becomes z, partial against y is minus 2, and 0. Yeah, that's it. Div f, divergence of f becomes z minus 2. So what we end up getting is z minus 2 dv. But when you look at it, we are looking at sphere. Since this is sphere, it's calling for spherical coordinate system. So what I'm going to do is, first one I'm going to write down z here. Z dv minus 2. But when you look into the second portion, that's the volume of the sphere, which is 4/3 pi r, which is equal to 2 cubed. So that's 8/32. Okay, so we get, so this portion becomes negative 64 over 3 pi. So that's what we end up getting for the second part. Let's calculate the first part here. In order for us to do that, I'm going to write this one as z is rho cosine phi, and then dv is what? Rho squared sine phi. d rho d phi d theta. And rho goes from 0 to 2, and 0 to pi, and 0 to 2 pi. Alrighty, so first, that's 2 pi, that's done. Now, what I'm going to do is, I'm going to look at the phi. Oh, wait a minute, that's kind of nice. Why? Because we have 0 through pi, and then cosine phi, sine phi, d phi, and 0 through 2, rho cubed d rho. But when you look at this, how about this factor right over here? This is the double angle formula for sine, except that I don't have 2 in the front. So it becomes, I can rewrite this one as pi, and then I'm going to borrow 2 inside. 0 through pi, and then sine of 2 phi d phi. And then I can bring this one down here, whatever that is. But when you look at it, what do you realize? 0 through pi, the sine of 2 phi completes one cycle, like this. So whatever this area and whatever that area, that cancels away from 0 through pi, which means that's equal to 0. So entire first portion is equal to 0, leaving us negative 64 over 3 pi is our final answer. All right, with that one, we're going to close up. I'll see you later.